Hello students, this is Dr. Sanjay Kumar Sahu. Welcome to the video lecture 3 of module 1. In last video lecture, we studied about intrinsic semiconductor. For intrinsic semiconductor, we learned that the conductivity of an intrinsic semiconductor largely depend upon temperature. So, at room temperature, the conductivity of an intrinsic semiconductor is limited. Therefore, it's not advisable to make devices using intrinsic semiconductor, because if you need a higher conductivity for those electronic devices, you will have to increase its temperature. At room temperature, that device may not work properly. The second problem with intrinsic semiconductor was that the conductivity of intrinsic semiconductor is very much sensitive to temperature changes. If you are changing the temperature to a little amount, the conductivity of the intrinsic semiconductor will change. This shows that if you are making devices out of intrinsic semiconductors, then those devices will be very much temperature sensitive, and it will not be easy to deal with such kind of devices, electronic devices, for our application purpose. These were the main reasons why we tried to dope an intrinsic semiconductor to increase its conductivity without changing the temperature. These doped semiconductors were called as extrinsic semiconductors. And in last class only, we discussed about various procedures of doping, and we discussed that depending upon the valence electrons, number of valence electrons of the dopant atoms, we can have various kind of extrinsic semiconductor. If the dopant atom will be pentavalent, then we will get a type of extrinsic semiconductor which is called as N-type semiconductor. If the dopant atom will be trivalent, having 3 valence electrons, then we will get a extrinsic semiconductor which is called as P-type semiconductor. In today's class, we will discuss in detail about these P-type and N-type semiconductors. So, now let us discuss N-type semiconductor first. When a semiconductor of group 4, which is tetravalent, having 4 valence electrons, such as silicon or germanium, is doped with a pentavalent impurity, group 5 elements such as phosphorus, arsenic, or antimony, a N-type semiconductor is formed. Now let us consider, for example, the germanium crystal is doped with arsenic as shown in the figure below. In this figure, as you can see, this is a germanium crystal, and all germanium atoms are having 4 valence electron each, and one of those germanium atom has been replaced by an arsenic atom whose number of electrons are 5. Now what will happen? Out of these 5 electrons of arsenic, 4 electrons will make covalent bonds with the 4 nearby germanium atoms, like this, and 1 electron is left behind. Now for this electron, the arsenic atom and the rest of the 4 electrons will behave as atomic core. That's why this electron will be loosely bound to the atomic core, and hence the ionization energy required to ionize this arsenic atom will be very less, since this extra electron will be loosely bound to this atomic core, because the atomic core has already fulfilled the octet rule. It is not requiring the 5th electron. That's why the force of attraction between this atomic core and this extra electron will be less, will be decreased. And due to that decrease in force of attraction, this electron will be loosely bound, and you require very less amount of energy to ionize this electron. That means if you will supply a very small amount of heat, then this electron will be freed from the foundation of this arsenic atom to conduct current. In other sense, we can say that this arsenic atom has donated one free electron to the core of the crystal, because you require very little amount of energy to ionize this arsenic atom to get rid of or to make this fifth electron free. Now, what will happen if I will supply heat to this crystal? Three things will happen. First, one excitation process will happen in which one electron may come out of this covalent bond between germanium and germanium or germanium and arsenic, and it will be freed. At the same time, one hole will be generated. So, one excitation process will happen in which one free electron will be generated in the conduction band and one free hole will be generated in the valence band. The second process will happen, whatever will happen is this fifth electron of arsenic will go up to the conduction band and it will be freed, and there will be no corresponding hole in the valence band for this fifth electron of arsenic atom. There will be no corresponding hole in the valence band. And the third process, whatever will happen is there will be recombination also. When there will be excitation process will be there, at the same time some recombination will also take place in which one electron from the conduction band will come back to the valence band to recombine with the hole and make this covalent bond intact. These three processes will take place when you will supply heat to such a crystal which is doped with arsenic. Now, in terms of band diagram, if you want to see, this is the band diagram. In terms of band diagram, this is valence band, this is conduction band, and the band gap between this valence band and conduction band is 0.74 electron volt, which is equal to the band gap energy of germanium semiconductor. Now, in this band diagram, this is the energy level of this donor electron. Since we discussed this donor electron will be very loosely bound to this arsenic atom, its energy level will lie very near to conduction band, so that with very little amount of energy it will be excited to conduction band for the purpose of conduction. The difference between this energy level and conduction band, lowest level of conduction band, is 0.01 electron volt, and this level is called donor level. Since arsenic is called as a donor atom, this energy level is called donor level. Now, the fifth electron of arsenic is sitting in the donor level, and with very little energy, very less than room temperature or 1 degree Celsius or 2 degrees Celsius, it will go up to the conduction band. And if you will further increase the temperature, then some electrons from the valence band will move to the conduction band. Now, these electrons which are coming from valence band to conduction band are called intrinsically generated electrons. These electrons which are coming from valence band to conduction band are called intrinsically generated electrons, for which there will be corresponding holes in the valence band. But for the electron which is generated or which is coming from this donor level to conduction band, there will be no corresponding hole in the valence band. Please note that those electrons which are intrinsically generated by giving thermal energy, for them there will be corresponding holes in the valence band. For those electrons which are donated by the impurity atom, for them there will be no corresponding holes in the valence band. Now let's have a recap what we discussed. When we are doping a pentavalent impurity atom to a germanium or silicon crystal, the force of attraction between the fifth electron and the positively charged impurity ion, this arsenic ion, is weakened. As a result of that, the energy state corresponding to the fifth electron is in the forbidden gap and slightly below the lower level of conduction band. Due to the decrease in the force of attraction between the mobile electron and the positively charged impurity ion, the energy level corresponding to the fifth electron is in the forbidden energy gap and slightly below the lower level of the conduction band as shown in this figure, which is 0.01 electron volt. This energy level is called donor energy level or donor level, and the impurity atom is called donor atom because it is freely giving one free electron for the purpose of conduction. That's why it is called donor atom. Now this energy level is very small, which is equal to 0.01 electron volt for germanium, which is very less in contrast to 0.74 electron volt. This 0.74 electron volt is the band gap energy for germanium, and this 0.01 electron volt is very much less than that 0.74 electron volt. That's why it is very easy to transfer a electron from the donor level to the conduction band rather than an electron from the valence band to the conduction band. To transfer an electron from the valence band to the conduction band, we require at least 0.74 electron volt of energy. Whereas to transfer an electron from this donor level to conduction band, we require at least 0.01 electron volt of energy, which you can get very easily by supplying a very small amount of heat or by increasing the temperature to a very small value. Now, a small amount of energy provided due to the thermal agitation is sufficient to detach this electron, and it is ready to conduct current, this electron. That's why N-type semiconductor is also called as donor type semiconductor. Now let us discuss what is a P-type semiconductor. When a semiconductor of group V tetravalent such as silicon or germanium is doped with a trivalent impurity, group 3 elements such as arsenic or boron or gallium, a P-type semiconductor is formed. For example, let us consider germanium is doped with indium as shown in the figure below. Now in this germanium crystal, one side, vacant side, is doped with an indium atom. Now germanium is having 4 valence electrons, whereas indium is having 3 valence electrons. Now in an attempt to get stability, both germanium and indium will try to make covalent bonds with each other, and in that attempt one deficiency of electron will be realized at one place, because indium is having 3 valence electrons and it require one more valence electron to satisfy the octet rule. Eventually this deficiency of electron or hole will try to pull nearby electrons to satisfy the octet rule. The energy level of this deficiency of electron or hole is very near to the highest level of valence band. In terms of band diagram, now in this situation, if we will supply heat, 3 processes will take place. In one process, one excitation of electron will take place from the valence band to the conduction band, in which one covalent bond between germanium and germanium or germanium and arsenic indium will be broken and one electron will be excited to the conduction band. At the same time, it will leave a hole in the valence band. In second process, one electron will move from the valence band or any of these covalent bond to fulfill the octet rule of this valence electron or this indium atom, this impurity atom. To satisfy the octet rule, this hole will pull up one electron from the nearby atom. That is the second process. In third process, one recombination will take place in which one electron from the conduction band will move back to the hole in the valence band to recombine with it to satisfy the octet rule. As a result of these three processes, there will be corresponding electron to each hole in the valence band if the electron or if the hole has been generated intrinsically. If the hole has been generated intrinsically by exciting one electron from the valence band to the conduction band, there will be a hole corresponding to each such electron, or there will be an electron corresponding to each such holes. But if a hole is created in the valence band just by moving an electron from the valence band to this acceptor atom energy level, then there will be no corresponding electron in the conduction band. To understand this more clearly, let us consider the band diagram. In this band diagram, this is the valence band, this is the conduction band of germanium, and this is the band gap which is 0.74 electron volt, and this is the acceptor energy level. This is the energy level of indium atom, and that energy level is having one hole which is given by this acceptor atom, which is the indium atom. Since this hole has a tendency to accept an electron from the valence band, that's why this is called an acceptor atom, and that's why this energy level is called as an acceptor energy level. The difference between the acceptor energy level and the top of the valence band is very small, that is equal to around 0.05 electron volt. Since this energy is very less, with a very little amount of heat energy, this hole in the acceptor energy level will be able to pull up an electron very easily from the valence band, like this. Now, in that case, in that event, we can say that the hole has been transferred from the acceptor energy level to the valence band, or the hole has sink to the valence band. But this is not the only possibility. The other possibility is that one electron may get excited from the valence band directly to the conduction band, and in that case there will be a corresponding hole in the valence band, and this charge carrier, this electron and this corresponding hole are called as intrinsically generated charge carrier, and this hole is known as hole given by this acceptor atom. So, this hole is given by acceptor atom, and this hole is generated intrinsically by excitation of electron from valence band to conduction band. At the same time, some recombination will also take place. As a whole, here the holes are generated due to two reasons. One is due to intrinsically generated electrons by exciting electrons from valence band to conduction band, and another hole is given by the acceptor atoms, whereas the electrons are generated only due to intrinsic region by exciting electrons from the valence band to the conduction band. Therefore, the number of charge carriers here, the number of holes here is more than the number of electrons, because the holes are generated because of two regions. Now, let us have a recap of these things. The hole which is deliberately created may be filled with an electron from the neighboring atom, creating a hole in that position from where the electron jumped. Therefore, the trivalent impurity atom is called an acceptor atom. Since the hole is associated with a positive charge moving from one position to another, therefore, this type of semiconductor is called p-type semiconductor. The acceptor impurity lies on an energy level just above the valence band. This energy level is called acceptor level. The energy difference between the acceptor energy level and the top of the valence band is much smaller than the band gap, so that with a very little energy, electrons from the valence band can easily move to the acceptor level by being thermally agitated. Therefore, the p-type semiconductor is also called as acceptor type semiconductor. Now, since in p-type semiconductor holes are generated due to both acceptor impurity and due to thermal agitation or due to intrinsic region, the number of holes is always greater than the number of electrons. And if you increase the acceptor impurity, concentration of acceptor impurity, the conductivity of the semiconductor will also increase, since the number of holes will increase. And since the number of holes is more here, they are called as majority charge carriers. In case of p-type semiconductor, holes are called as majority charge carriers, whereas electrons are called as minority charge carriers. And number of holes is very greater than number of electrons. And it is very easy to show that in case of p-type semiconductor also this relation holds good. What is this relation? The product between number of holes and number of electrons is equal to a constant, which is nothing but the square of the intrinsic charge carrier concentration. Now, let us discuss the difference between intrinsic and extrinsic semiconductor. Intrinsic semiconductor belongs to group 4. They are pure semiconductor. They belongs to group 4 of periodic table. Whereas extrinsic semiconductor are doped semiconductor, where group 3 or group 5 elements are introduced to group 4 elements. Why we chosen only group 3 or group 5? Because the size of the atoms of group 3 and group 5 elements will be more or less same as the size of the atoms of the group 4 elements. So, it will be easy to dope a group 4 element with atoms of group 3 and group 5 elements. If the size of the atoms will be too much different, then there will be lot of defects and it is not possible to dope nicely. That is the reason why we chosen only group 3 and group 5 elements. In case of intrinsic semiconductor, the conductivity is very less. The conductivity, whatever conductivity you are getting, those are due to intrinsic charge carriers generated thermally by exciting electrons from the valence band to conduction band. Whereas in case of extrinsic semiconductor, the conductivity is greatly increased by adding the impurity. In case of n-type semiconductor, n-type extrinsic semiconductor, the conductivity is increased by adding pentavalent impurity where an extra electron will be donated by the impurity atom. Whereas in case of p-type semiconductor, the conductivity will be increased by doping with trivalent impurity where an extra hole will be donated. That means an electron will be accepted. That is why p-type is called as acceptor type semiconductor and n-type is called as donor type semiconductor. It is called donor type semiconductor because it is donating an electron, and whereas p-type is called as acceptor type semiconductor because it is accepting an electron. The intrinsic semiconductor's conductivity increases with the rise in temperature. It is temperature sensitivity. The conductivity of intrinsic semiconductor is temperature sensitive, whereas the conductivity of an extrinsic semiconductor is largely dependent on impurity added, amount of impurity added. If you are increasing the impurity amount, then the conductivity will increase. Temperature has a very little role in the increasing or in the conductivity. If you are increasing the temperature, the number of electrons will increase, but at the same time number of holes will decrease to keep the product N into P as a constant. The fourth point is the number of holes is always equal to the number of free electrons in case of an intrinsic semiconductor. Whereas in case of an extrinsic semiconductor, if it is N type, the number of electrons is greater than the number of holes, and number of electrons are called as majority charge carriers and holes are called as minority charge carriers. And if it is p-type semiconductor, the number of holes is greater than the number of electrons. Here holes are called as majority charge carriers and electrons are called as minority charge carriers. These are the four most important differences between intrinsic and extrinsic semiconductor. Similarly, let us discuss the differences between a semiconductor and a metal. Now, in case of a semiconductor, the semiconductor behaves like an insulator at 0 degree Kelvin. Its conductivity increases with rise in temperature, whereas the conductivity of metal decreases with rise in temperature. Please keep it in mind. In case of semiconductor, the conductivity increases with rise in temperature because with the rise in temperature, the number of electrons excited from the valence band to conduction band will increase and hence its conductivity will increase. But in case of a metal which is a conductor, the conductivity decreases with rise in temperature because if you are rising the temperature, the random motion of the free electrons will increase and hence their drift velocity will decrease. That is why the conductivity will decrease. In case of semiconductor, the conductivity increases with rise in potential difference applied. In case of a semiconductor, if you are increasing the potential difference, then the conductivity will increase. But in case of metal, the conductivity is an intrinsic property of the metal and it is independent of the applied potential difference. But in case of semiconductor, the conductivity is not an intrinsic property, it is decided by the external potential also. You will realize this point later on when you will study about p-n junction. Now, the conductivity of semiconductor does not obey Ohm's law, or it obeys partially at certain point, at certain potential difference it obeys Ohm's law, at other points it do not obey Ohm's law. This point also you will get clear about when you will study about p-n junction diagram. Whereas in case of metal, the metal obeys the Ohm's law very nicely. The fourth point is, in case of semiconductor, if you are doping the semiconductors with impurity, firstly it increases the conductivity. Whereas if you will make different alloys by mixing one metal with another, it will decrease its conductivity. In contrast to a semiconductor where if you are doping the semiconductor with impurity, then its conductivity increases. These are the four important distinctions between semiconductor and metal. Now we came to an end of this module 1. Now before concluding, let's discuss about the outcomes. What outcomes you got? Now after learning this entire module, you are now able to answer how various energy bands form during the process of crystallization. Second, you will be able to answer how these energy bands play a role in classification of solids into various types like insulator, conductor, semiconductor. What are conductors, what are insulators, and what are semiconductors, and what are the typical properties in terms of conductivity and resistivity. Also, you will be able to answer what are intrinsic semiconductors and how electrical conduction takes place in intrinsic semiconductor. Further, you will be able to answer what is effect of temperature on the conductivity of intrinsic semiconductor. How, if you are changing the temperature, the conductivity of an intrinsic semiconductor is changing, that you will be able to answer. Further, you will be able to answer what are various procedures of doping an intrinsic semiconductor to get extrinsic semiconductor. What are those procedures? Like epitaxy, ion implantation, diffusion. What are those procedures by using which you can get an extrinsic semiconductor from intrinsic semiconductor? Also, you will be able to answer what are extrinsic semiconductor, what is a p-type semiconductor, what is a n-type semiconductor, how they are formed, what are the different impurities you have to mix with the intrinsic semiconductor to get a p-type or n-type semiconductor. Also, you will be able to answer what are majority and minority charge carriers in case of an extrinsic semiconductor. If it is a n-type semiconductor, what are the majority charge carrier and what are the minority charge carriers? In case of a p-type semiconductor, what are the majority charge carriers and what are the minority charge carriers? You will be able to answer that. Also, you will be able to answer what are the effects of temperature and doping on the conductivity of semiconductor. You will be able to answer if you are increasing the doping concentration or if you are decreasing the doping concentration, how the conductivity of an extrinsic semiconductor is changing. That you will be able to answer. Also, you will be able to answer the differences between intrinsic and extrinsic semiconductors. Also, you will be able to answer between the differences between p-type and n-type semiconductors. You will be able to answer the differences between metals and insulators, metals and semiconductors. So these are the various outcomes that you should get after learning this module. So we are at the end of module 1. Next we will start module 2, where we will try to discuss, we will try to make some devices out of these p-type and n-type semiconductors. Thank you.